All right, we're back. We are on page 8 of Calc AB Notes 6, and it kind of starts with a nice summary of the derivatives of the inverse trig function. So let's write these down. So there's two different versions that we're going to write down. We're going to write down just in the left-hand column, it's a function of x, and in the right-hand column, we know that u is a function of x, so we're going to write down the chain rule version. I think it's really useful to look at the chain rule version of these because more often than not, you actually see them that way. So you want to memorize them for sure, but then just keep in mind the chain rule is a thing and you're going to use it from time to time. So these, because we memorize them, can kind of just write them down. So I always write the derivative of arctan is 1 over 1 plus x squared. The reason I do that is that later in life, you're going to deal in Calc 2. You're going to deal with infinite geometric series, and the sum of an infinite geometric series looks an awful lot like the derivative of arctan, and they're kind of related in a lot of problems. So I just got used to writing it that way, and I basically always do. And then secant is, of these, by far the least important. And it kind of looks like arcsine, but it's like you flip the things. You got that absolute value of x there. That looks unlike arcsine. And then x squared minus 1. That's the whole thing. So if we do the chain rule versions, we're going to get what's the best way to write this? I'm going to write it as 1 over the square root of 1 minus u squared times du dx. So whatever du dx is, you got to multiply it in by the chain rule. And then you get 1 over 1 plus u squared times du dx. So sometimes you'll also just see u prime in the numerators. Totally fine. However you want to write it. These are just for your information more than anything else. The absolute value of u, square root of u squared minus 1 times du dx. This just keep you thinking about the chain rule because it happens all the time. So these are the ones you got to really, really memorize. So really it's this column needs to be memorized. I wonder how thick I can make this highlighter. Something a little faster, hopefully. There we go. This column, gotta know it. Backwards and forward, literally backwards and forwards. When you see the derivative, recognize the function. So we got those down. So let's see this question. Find a way to use implicit differentiation to find the derivative of y equals 5 to the x. So find a way to use implicit differentiation. So I'm going to think about this as if I have y equals 5 to the x. Well, I kind of know a way that I can get exponents down from their, I don't know, their lofty perch or whatever, with natural logs, right? Because if I take a natural log of both sides, then the exponent becomes a coefficient. That might be useful. And then when I find the derivative of natural log of y, I'll be using implicit. So this feels like the right thing to do. So I'm going to take natural log of both sides, natural log of 5 to the x, and then that means the natural log of y is equal to x times the natural log of 5. So exponents become coefficients. You use that property a lot in calculus. And now I'm going to take the derivative with respect to x of both sides. Should be equal to the derivative with respect to x of x times the natural log of 5. So don't forget the natural log of 5 is just a number. It doesn't look like a number that you're familiar with because you don't know what the natural log of 5 is probably. But it is just a number. So on the right-hand side, it's just going to be x times a number. So we know how to find that derivative. Don't freak out about that. On the left-hand side, the derivative of natural log of something is 1 over that thing times the derivative of that thing. There you go. The right-hand side, it's just, if you had to take the derivative of 3x, you would just get 3. The derivative of x times the natural log of 5 is just the natural log of 5. So I'm going to multiply across, get y times the natural log of 5. Now I don't want to stop there because the original problem, we have y as a function of x. So I'd prefer, if I can, to get the derivative to be a function of x as well. But since this is here, whoa, way too big. I forgot that I had gone crazy on that last thing. This is here, and then we also know that this is true. So we can rewrite it and have our final answer. Did I erase something? I think I did. As dy dx is 5 to the x times the natural log of 5. So is this consistent with e to the x? That's a question we want to answer. First, let's do this. So find a generalization this is going to be the exact same process. So let's just get to it, right? So the natural log of a, nope, the natural log of y is equal to, I'm going to do the two steps at once. I'm going to say it's x times the natural log of a. And then the derivative of both sides with respect to x, which I often skip showing this step. And I think it's a bad habit, so you should be better than me. Like this. All right, so it's going to be 1 over y times dy. So you always have this available to you, like this process. You want to memorize this, though, because it's a really common thing to deal with. So we go up here, and we have dy dx is equal to y times the natural log of a. Okay, but we know, just like in the last one, that y, kind of scrolled on me there, y is equal to a to the x. So we'll make our substitution. So we get dy dx is going to be a to the x times the natural log of a. So if y is equal to a to the x, the derivative is a to the x natural log of a. So now the question is, does e to the x apply, right? So let me like box this off, and I'm just going to do a little weird thing on the side here, see if it works, right? So if y is equal to e to the x, I know the derivative. Do I know the derivative? You know, I don't know if I know the derivative of e to the x yet. I think I do. Note 6, you must know it by now. So I'm doing these all out of order because I'm just like kind of picking and choosing where I want to like make the notes, make videos for the notes. So that's why I'm a little confused about what you may or may not know. You should know the derivative of e to the x at this point. So we would say dy dx is e to the x because we have that memorized. What if we use the rule though? The rule says that dy dx should be e to the x times the natural log of e. Are these equivalent? I'm going to say yes, these are equivalent because the natural log of e is equal to 1. So it works. It works for e to the x. It works for everything. So you have to remember it. It's nice. It's comforting to know that, like, in the event that you forget, it's really not hard to work it out, but it's definitely worth memorizing. So here we have the derivative of a to the x should be a to the x natural log of a. Now, a chain rule version of this kind of, it starts to, this is why you just want to know the chain rule, right? So it's going to look a little bigger. A to the u times the natural log of a times du dx, right? So the chain rule, you always times the derivative of the thing. So the derivative of a to the something is a to the something natural log of a times the derivative of that thing. So that's where we go with that. Now here it just tells you like sort of why it's really beneficial to remember the derivatives of these things. So you are likely to forget. This is super important. The natural log of a gotta be there. What you want to be able to do is you want to be able to go backwards, right? From knowing that the derivative is 3 to the x to what function? What function would have a derivative that is 3 to the x? Well, since we know the derivative of 3 to the x is 3 to the x natural log of 3, there must have been a 1 over natural log of 3 to begin with, right? Because if I find the derivative of this, 1 over the natural log of 3. 1 over the natural log of 3 is just a number. So that's a constant. So the derivative of that, well, so we're not going to use a product rule because that's crazy. We're not going to use a quotient rule because that's crazy because it's just a constant. So here we'll get the derivative of 3. So there's constant multiple. The derivative of 3 to the x is 3 to the x times the natural log of 3. And then the derivative of c is just 0. So this gives me just 3 to the x, which is exactly what we had over here. And so this is part of why you want to have it memorized. You want to be able to look at something and think like, what function is that the derivative of? And if you have this memorized, you can do it pretty easily. If you don't have it memorized, things start getting harder and harder. So make sure, as I tell you to memorize things, that you're actually doing it. But anyway, that like adds to our list. So we've got derivatives of general exponentials. Derivative of e to the x is e to the x. Or you could think of it as e to the x times the natural log of e. No one really thinks of it that way, but the natural log of e is 1, so it's reassuring that it's working. And then we kind of summarize these. So arcsine, arctangent come up all the time. Make sure you know them. Arcsecant, far less common. And then any of the cos just have a negative. So the derivative of arccosine is negative of the derivative of arcsine. Derivative of arccotangent is the negative of the derivative of arctan. That's why you want to know arcsine and arctan. They come up by far the most. The other ones like exist, so you should be aware of them, but they're not the ones you want to really focus on. But anyway, I'm going to wrap this up. I'll come back in the next video and I think finish these notes. So I will see you there. And I hope you are finding this helpful.